Good morning, good afternoon, or good evening, wherever you are in the world, welcome. My name is Zaim, and on behalf of the entire Materia team, I would like to thank you for joining us for the second session of the Advanced Finite Element webinar series. Today's topic is Advanced Finite Element Problems with choosing correct material properties, a subject that lies at the very heart of precision, performance, and reliability in modern simulation workflows. Our goal in this series is to go beyond theory and explore how correct material property selection can dramatically improve the accuracy of the simulation results, reduce the design repetitions, and ultimately support innovation with confidence. Today, we'll walk through the technical challenges of material property selection in finite element models, from elastic to plastic behavior, and explore how tools like total materia can support informed decision making using accurate, traceable, and standardized material data. Please feel free to drop your questions in a chat. During the session, we'll have a dedicated QA at the end. Once again, thank you for joining us, and let's dive into today's topic.
Okay. So we have a second webinar of the webinar series, by the way. So let me introduce myself once again, if it is okay. So my name is Erdido, and I have 12 years experience on FAE. So expert level of Abaqus implicit and explicit analysis, and also Nastran and Elastina. And of course, dynamic thermal behavior of materials and optimization loops with Python scriptings. I have 3 years of mentoring and 5 years of project management experience background. So, Bart, your turn.
Hello, everyone. I'm Bartu. So I recently graduated from Cranfield University, Advanced Lightweight and Composite Structures. I'm a junior structural analysis engineer. I have a experience in Abaqus implicit explicit analysis and Elastina, as well as the composite materials and structures, design and analysis of metamaterials, and machine learning, deep learning for engineering. Also, I had a really good training on my MSc about the crashworthiness applications, and I have a pretty decent experience in impact engineering as well. So thank you for joining our webinar.
Okay, and this is the second webinar of the webinar series, which is the much more advanced from the previous one. The previous one is just the introduction of the FAE softwares, such as the basic material selections, but today will be a little bit advanced topics we will talk about it. And the last one is the third one is the much more detailed will be. So basically, I will say that you can see my picture or my video under the right down of the screen. Let me check. I think it's paused because of the technical issue, I think. So, okay, let me just pause a second, and I will just erase my camera from the right side of the presentation. Okay. Apply to slides. Yeah. Again, sorry about that. Okay, this will be much more better. Okay, so here the agenda. So we will talk about the general workflow of an analysis, and we will talk about also parts, rigid parts especially, and another nonlinear behavior, which is contact. We will talk about it, and advanced material characterization for forming, which means the plasticity models. We will talk about it, and also integrated with the Excel files and the Python scripts for the characterization methods. And Zaim also will show us the extended search live demo in total Materia. And also Bartu will speak about the composite material characterization. And then thermal effects of materials we will continue. And the last one is the forming simulation in Abaqus. So, and the workflow we are looking for it. So the parts actually and the property and assembly we continue. So today we will talk about this little bit parts session and a little bit the interaction session. I mean the contact area especially. So what are parts? That the parts are actually we are talking about the formal ones, but also we need to consider about the rigid parts, which can be included in a forming simulation. For example, a die. So we can model as a discrete parts which has a surface mesh, or we can continue with the analytic rigid parts, which you can see in here. So if you want a more precise solution, that you can go with the analytical rigids. So also, if you have a really big strains and a really big deformation in your model, you can choose the Eulerian solution, which can be modeled as the coupled Eulerian-Lagrangian methods. So, but also geometry import and repair could be much more need to pay attention, because you don't want to all the details in your finite element model. So you need to simplify some of the regions actually. And also you need to choose which property you need to imply on it. I mean, you have a real part like that, the left side, and you can choose which one could be fit my solution actually. So if you look about the contact behavior, because of the very nonlinear challenging effect, we can assume. Previous webinar, we have talked about the geometric nonlinearity, just a little bit contact, boundary linearity, I mean, and a little bit material linearity. But this webinar will be a deep dive on this nonlinear effects. So basically, we have three regions need to be focused. I mean, this is the properties, domain, formulation, and controls need to be taken into account. So this is the challenging part, that is the, as you can see, in the contact properties have a two kind of behaviors that need to be considering. So one of is the normal behavior, which means the approaching the contact and the contact solution, if it is okay or not. And the second one is the tangential behavior, which can be assumed as a slippery or sticky condition. So other things is the contact pairs, that which contact surfaces can be made, and the other is the roles. For example, master and slave surfaces need to be chosen, and the discretization method, I mean the node to surface like that, and the traction approach also, a fine sliding, small sliding like that. But in this webinar, I need to focus that the contact reinforcement methods, which is really hard to solve the problem. I mean, before the contact, you can see that there is no penetration and there is distance between part and the wall. And at that point, it's a little bit very small timing area. Your stiffness can be really high, that cannot be convergence with the Norton-Rimson method. So in this case, some enforcement methods comes up. So the one is the penalty stiffness. Of course, there is a, how can I say, there is a error indicator in this contact pressure. We already know about it. So, but if we implement on a stiffness at the beginning of the contact and the penetration, we can solve it easily, but we need to check it if it is really behave normally or abnormal. So there is another method that can be fit in the linear and the nonlinear approach. Somehow it can be, say, augmented Lagrange solution. So it could be fit by the nonlinear problem like this one. So the both methods can be applicable if you are doing well, actually. So if you are knowing what you are doing at the finite element methods, you can easily implement on it, actually. So here is the actual direct enforcement and the penalty methods, disadvantage, advantage, and you can actually read it and you can get this presentation from Zaim, of course. And the contact outputs, which is the last thing I would like to say about the contacts. For example, if you have a contact and you have seen the contact pressure like this, and you must check the contact error indicator in Abaqus to know that if it is okay or not. I mean the meshing criteria. So if you don't have a like that contact pressure, so you are looking for the maximum contact pressure area, but you cannot find it. When you check the contact pressure error indicator in your screen, so it means that you need a finer mesh to predict maximum contact pressure, actually. So that's why you need to check your contact pressure and error indicator at the end of your solution. So if you go for the material characterization for forming, we will speak about the engineering versus true stresses, material test data handling. We have a bunch of exas files and Python scripts about it. And also elasticity and yield point investigation, importance we will need to discuss. And also the hardening curves, Ludwig-Holloman, and I also put this Johnson-Cook material plasticity model. But also we can speak about it, the Swift-Hook, Sharby, or voice, whatever you want. If any questions can be written or via chat, I can easily to reply on it. And the material-based convergence mechanism, we will talk about it, and the temperature and strain rate effects, actually. So engineering versus true stress is interesting phenomenon that I just want to say one word about it. If you are doing a finite element analysis, you need to considering about all your test data, all your material data should be true stress and logarithmic strain. I mean true stress strain. So if you have an input, you need the true stress strain. If you have an output, you will read the true stress strain. Unless if you have a hyperelastic material, if you have a really big strains that can be softening, not hardening, like the titanium at the 800 degrees, something like that, or changing the crystallization area, this one is the cannot be go with the true stress. You need to go for the engineering stress, actually. So this is the key point of the which one could be selected, actually. If you have a low stress like metals, steels, or aluminum like that, you can go for easily true stress. So if you have a test data, you need to consider about it the conversion of from the engineering stress and the true stress. They have also some Excel sheets for it, and you can try to check it. Before we go, you need to understand that if you are implying the true stress, you need to identify the ultimate ultimate tensile stress area. But if you are going for the forming simulation, like the height strain values, you cannot go for the stress values. You need to go for the elongation and strain levels. Or if you have an impact analysis or something like that, you need to go for the initial energy, actually. So you will see that the Excel files, I will also share with Zaim, and you can get it from Zaim, that they have nominal stress, nominal strain, engineering stress, logarithmic strain, true stress areas, and some Young modulus has been calculated in here. You can directly calculate your modulus of elasticity via nominal strain, I mean the test stress data, directly, because in lots of metals, converting to the engineering to the true stress is very low change. So it cannot any change at the end of the calculated modulus of elasticity. It could be both true. You have an assumption actually. So, but before you go that, you need to check your data. The differences, I mean the stress level is increasing or lowering. You need to check it before you calculate into your average modulus of elasticity, and you need to check your R-square value according to the average calculation. So, for example, some data is really bad that, as you can see, you have an engineering stress in here. It's a light blue curve. So basically, you are just investigating what are my modulus of elasticity, but you see that there is an error in here. So it's going for the negative strain. So you need to check your data. Maybe you can shift it, or you can just manipulate it, maybe. So you need to just grab it to the elasticity in here and the average values in here to check which modulus of elasticity need to be taken into account. So basically, if you have a material like this one, you can see that there is no specific yield area. This is not the yield, by the way, because this curve is not linear. So as you can see, if you have a material but you cannot find the yield point, you need to assume it. If you have a hot forming, so the higher temperatures, so you can basically go for the Holloman model, which means the directly the plastic area. But if you have a spring back effect, like a cold forming, for example, you need to identify your yield point and modulus of elasticity because of the spring back effect, actually. So before you go that, you need to understand which area can be fit or which line should I take into account as a modulus of elasticity. As you already know that this line, the tangent of this line, gives us the Young modulus. So if you talk about the plastic curves, so the left side is we can assume that the bilinear modeling. I mean, these are all the plastic strain x-axis, as you can see. So if you are defining a yield point and another ultimate point in here, this method can be easily go with the searching which material can be fit my model. But if you are looking for only the initial energy, for example, if you have an impact analysis, we go for the initial energy, which the area of the under this curve. So if you have a material that you already choose, or you are looking for the any, how can I say, any slightly different similar materials, that you need to go for the Holloman or Ludwig materials. Which are the differences is Holloman has a no yield point. I mean, I already talked about the hot forming area, so you can directly use this one. So you assume that I have no yield point at that temperature. I can easily go for the hot forming in that. So, but you need to also assume that really a temperature effect on a hot forming. In the cold forming side, you need to assume that there is a yield point, and you need to consider about the spring back effect. Actually, you can easily go with the Ludwig model, as you can see. So some I can page that this is the Ludwig Holloman hardening curve, like this one, but this is the actual differences. In the Johnson-Cook material model, you can see that this formulation also driven in here, as you can see. This is the Johnson-Cook material plasticity model. So in this area, this is the hardening curve, defines it, and this strain rate dependency, as you can see. This one is the strain rate reference value, and also the temperature side, as you can see. I have also some examples to calculate this strain rate effects and the temperature effects. Also, I will also share it, but I can mention about it, which it is. And that one, material-based convergence mechanism. In the previous webinar, we talked about a little bit this one. If you have a last stress strain point like this one, but you can sometimes get through the last point. So as a default, most of the finite element softwares, this could be a constant, linear, and the same stress level, but absolutely always going for the infinitely plastic strain domain. So this is really a big challenge to solve this convergence issue, because in this default value that you have no tangency, you have zero stiffness in here. But if you model as a linear extrapolation according to the previous previous data point, you can assume that there's a same tangential in here, and I will just put the last data point in something like here. So I can easily observe the logarithmic plastic strain, I mean the plastic equivalent strain, to check the last strain and the last elongation value, if it is okay or not. So you need to go for the equivalent plastic strain actually here. I don't want to mention about the hydrostatic and diverteric stress or Leibniz equations. We don't have much time actually, but just think about it. Okay, the last one is the material characterization. We can say that most of the materials has the increasing temperature lowers the curve in the stress strain area, and also lowers the modulus of elasticity, as you can see, most of the time. But if you have a recrystallization effect or the different material you are facing it, it could be dependent on the which crystal you are looking for. You need to also consider the latent heat effect actually. On the right side is the, as you can see, strain rate increasing. If the strain rate increases, I mean the much more faster deformation in your model, you need to consider that increasing the strain rate increase the ultimate stress area. But most of the time, it's constant the modulus of elasticity. Just a little bit changes actually. But you assume that there will be no differences actually. And I would like to mention about the Python scripts and the material characterization. I will give you the Python script freely and the other exas. I want to mention about the exa solution first. Here is the stress values, the test data. You can assume that this one, and this one. This is the reference strain rate effects, and this is the calculation of the according to the Johnson-Cook material model, and the root mean square error calculated according to these values. So in Excel, you can go for the prediction like file, options, add-ins, and the Excel add-ins. You can check the solver add-in in here, and then use data section and the solver in here. As you can see, you can change the solving method and the constraints, and also give the objectives, minimize this total of root mean square errors, and the changing by these values actually. So if you get the Excel file, you can directly use it and regenerate it actually easily. So at the end, you will have the coefficients of init, and you can directly put it as an input in Abaqus in these values actually. So another example that calculation R values. We have maybe mentioned about the criteria as an anisotropic plasticity. And here is the calculation for a lamina. And this is the Abaqus input. You can easily directly put in here. There is some example in here, calculated R values. And this is also a Swift-Hochschild stress strain model. Another example, another advanced material model. We can just assume it. This is a combination of the Swift and the Hochschild actually. These both materials are actually different, but this is the combination of it. So another material model can be matched by voice. Voice is the really good player for the not hardening, for the softening materials like titanium in a higher temperature effects. If you have a really big strains, that it could be grain level changing and the softening occurs actually. So another that conversion of the engineering stress strain to true stress strain, as you can see in here, you can directly paste it. And how can I say, sample material data, check it. There is a really a calculation of Young modulus and differences, averages. So the curves, as you can see, predictions in here. The last one is the Python script I can mention about it. So for example, you have a 6 different strain and the 6 different stress values that written like this one. So you have also stresses in here written like this one. So you can just go and click the Python script and it asks how many stress strain data you have. I have 6 stress strain data. What is the last strain value? It could be a prediction, not the exact value. So like this one, and it says the sensitivity. This is a curve fitting actually, not the rocket science. So when I click it, I can easily get the material calculation, fit this all the curves in here. As you can see, there's actually lots of data in here. So at the end of the script that we have this material text, so Kn values, which is related with the Ludwig model actually, and also the yield point. You can directly use these ones. Scripts and the Excel data, you can directly manipulate it in here. So you can just change the, how can I say, change the equation, which model do you want to go on, and easily apply it. So it is free to use. Don't need the crypto actually. So Zaim, it's your turn actually.
Thank you very much. So obviously, we need to understand materials elastic to plastic behavior and what is engineering versus true stress strain. We need a Lagrangian models of elasticity, aka Young's modulus, strain rates, hardening, strain rate, temperature, and all this data, right? So we basically need a reliable information source, obviously. So this is Total Materia. Some of you guys knows very well. I can see some of our attendees here, our users, and well, basically, this is how it looks like. It is very easy to use. Somehow, all you need to just type the numerical, alphanumerical material designation, or you can filter some material here in standards, so directly producer's data sheet. You can reach the standards list and you can make the advanced search, which material is suitable to your design according to mechanical physical properties. I'd like to show you an example as a material very well known, stainless steel from automotive industry. Well, here's the material card. Here's a lot of mechanical, physical properties, which Erdi just mentioned that the
Can I interrupt
temperature,
here, please? Yeah. For example,
temperature,
we need a temperature dependency
yeah,
values and the strain rate dependency values. Like we want to model Johnson Cook material model.
that's it.
So
So you
we are
you
looking
can
for
make
it.
basically see the yield strength values is changing while I'm clicking here. See, or tensile strength, and you know, so these are all depending. Directly, you can use check the details and graphs, or you can go dive into the detailed view. So many standard references here for 152 different conditions. Of course, same material as depend on which heat treated material we are talking about, which form of the material we are talking about, or what dimensions of the material we are talking about. Not only different mechanical physical properties, but the same material is behaving differently, right? So where you can do, check the whole these details about material. That could be an option, but we need some more detailed information like stress strain, right? Directly you can reach from Materia. You see, exclude bilinear diagrams. This is kind of
Can
a new features of
see that
Materia.
sorry
Exclude
for
from,
interruptions.
yeah,
So
please.
easily we can see that the strain rate dependency in here, the left side of the condition. In the
Yeah.
different strain rates, we can see that. So we can
Well,
implement it easily.
yeah, definitely. It depends on the design where you are going to use, including for the for mobility curves. It gives you high strain curves, forming limit curves, bendability, R factors for, pressing. As you can see, we have the strain rates here clearly, and this is the comment of the test. These tests have been made already. You can reach, by the way, if you want to search not only one particular material, but go dive into the extended range that you need high temperature strain rate values, or you want to filter very, very high strain rate values that you need, especially for crash simulation. I think Bart will agree that these are very valuable informations that we have. Like, let's say one particular material group that I received this question during this week, non-ferrous alloys. We need some material information, but in between actually 100 to 300 degree, how many materials that we have, we can easily check like thousands of materials. In the same time, you want to see tensile yield strength values of this material. You want very, very high tensile strength, or very, very high yield strength value, or impact strength, or hardness, whatever you want to see about the material, you can easily filter. You still can see the stress strain values if you have some fatigue information, or joints, and even direct supply information. I mean, Tolmateria have all this data because it's been 26 years. Tolmateria is online, so whenever you want to use Tolmateria, you can ask technical support. You can watch some short guided tour videos about it, or you can get directly technical support. I mean, there are a lot of things to say about Tolmateria, but I just want you to know that whenever you need, you can use, and whatever you want to find inside Tolmateria, we are ready to help. Is this all
One
I
last
want to
thing I
say?
want to ask Zaim.
Please.
Is it possible to check the stress strain data if it is engineering or a true stress data we are reading?
Well,
Yeah.
sure. Well, sure. It is all depends on the material, because of our quality certificates. Like Tomater is a reliable information source, right? So we cannot add any information without showing you any references here. If reference provides all this data, this test data, and different materials, different conditions, As you can see in this test, obviously, in detail, we have true stress strain and engineering stress strain. These are very important. You just explained us basically what is the difference when we can use engineering, when we need to go to true stress strain. So these are very, very important values. Plus, you can add to diagram comparison. We do have a lot of data. So that's all I want to say. Please continue, Erdi, and
Absolutely.
we want to hear more about details in finite element analysis.
Okay.
So your
So
turn, Marta.
yeah, all right. So I would like to start to what is the composite materials? The definition of composite materials is a combination of two materials with different physical and chemical properties. So in this session, as we know, there's totally really different composite materials, like as they're shown: polymer matrix, metal matrix, ceramic matrix, reinforced concrete. We will only talk about the polymer matrix composite and unidirectional, by the way. No, as you know, that there is a different kind of polymer matrix composite as well in terms of woven or knit. So yes, we can move on. Okay, we can move on, Ert. Yeah. So as you know, in 3D stress state, we have the constitutive relationship for isotropic materials, and it has two different engineering constants, independent engineering constants to model that. Go on, please. So, by the way, first we need to define the orthotropic material. So, orthotropic material actually is an isotropic material that exhibits distinct, I would say, mechanical properties along the three orthogonal directions, X, Y, and Z, we would say. So because of this, in order to model an orthotropic material, you need 9 independent engineering constants. By the way, I need to mention that this is all linear elastic. This is Hooke's law, by the way, as you know. Please go on, Erdi. So the question is, if the orthotropic, as you can see, it's a little bit challenging to model an orthotropic material. So is there any better or I would say more efficient approach? Yes. So when we are, by the way, when we're talking about the composites, it's a combination of lamina. Lamina is a one sheet of composite ply. So when you combine the sheets with different angles, you get laminate. So we can model one orthotropic unidirectional composite material as a plane stress, which means it doesn't have any outplane stresses. So it will give us an edge. I think it is really important to mention that sometimes when you're modeling a really big parts, like if you're modeling a aircraft fuselage, as you know that aircraft fuselages have a really thin composite laminates in the skin and the sandwich plates on the mid surface. So modeling like this is an appropriate way, because sometimes it becomes a really costly in terms of computational power. So we will discuss the plane stress laminate analysis, by the way. So please go on, Erdi. So first, as we know that we want to combine, or we can combine our composite material in different directions. So we need to distinguish that we have a material direction, so which means that our fibers are directed, like it's its material orientation, and we have our global coordinate system or global orientation. So in order to get from a composite material, maybe off-axis stiffness, you need to convert the material from the material properties. The material direction. You need to convert it to global coordinates.
Actually, we are.
So we will use transformation matrix. I will not deep dive it. You can always check it because we have other things to talk about. Go on, Andy, please.
Okay.
So this is no. I will only say one thing. Yeah. So this is the stress strain relationship, and this Q bar tells us that it is for a one lamina. It tells us the transformed stiffness matrix. It will become important, by the way. Please go on, Adi.
Mm-hmm.
So in order to the fundamental analysis for this kind of structures, we can use classical laminate theory. It's a really fundamental theory, and it is widely used for preliminary analysis as well, and it's pretty useful. So, but we have our assumptions in it. So we will say that our middle surface is always perpendicular. Our normal surface in the right, you can see it is always perpendicular to the middle surface. It's really important. It tells us that we don't have transfer shear stresses in plane out plane direction. Also, we don't have we will say that laminate's thin, so that we don't have in the z direction, we don't have other stress values as well. So the displacements are continuous, really small, and the laminate, the thickness will never change in this analysis for the laminate. Also, I need to mention that, yeah.
Sorry, I just want to interrupt. What if our laminate is really thick, and assuming that there is a slipping between the layers?
No, you cannot model.
Sorry, in this assumption, we are assuming that there will be no any slippery condition.
Yeah.
The fully elastic solution, we are assuming. And what if we have a thick laminate, and actually this assumption continues with the conventional shell modeling in finite element analysis. But what if we have a thick model and we are looking for the slipping between the slip condition between the layers?
No, you cannot model. You cannot model. You cannot look in the thick laminate.
This assumption we cannot model, actually. We need to go for the different continuous shell models, actually, maybe.
No, okay. You're asking. I was talking about the analytical solution for it.
Yes,
sorry.
Actually.
Okay. I misunderstand what you said. You're asking for FEM. Yeah, of course we can use continuum shell elements for model thick elements. It's thick laminates. But for this, we are actually what we're doing is we're just idealizing this structure as a 2D. So for this classical laminate theory, you cannot do it. But in FEM, you can use continuum shell, and you can actually do it. Yeah.
Oh, yeah.
So, yeah, we can go on.
All right.
Okay. So we need to start. We need to look for the equations of displacements in order to understand our behavior. So as you can see, we have three displacements. One of them is U, V, and W. W is the outplane displacement, and it is, as you can see, it is in a function of x and y. So it is induced by u and y. So from the moments and the normal forces which act on the plate. So as you can see, if we get differentiate the u the first equation, you will see that we have a rotation in-plane movement caused by rotation for the laminate due to bending. So at the end, in 13th, we will see that our global strain is about our mid-surface strains and the bending effects. So we can go on.
Mm-hmm.
So in classical laminate theory, we can say that in order to relate this stress-strain relationship, so we're using 2D structural lights, right? So first we need to look for how can we add forces and moments. So what we can do is we can, as you can see, as done in here, we can take a integral of sigma x, sigma y, and sigma xy in a thickness direction. So that we can get the equation like in 16th, and after that we can apply this equation, plug in this equation, and get 70, the equation 70, as you can see. From that, as you can see, we just related normal forces, the shear strains, and the curvatures. So we can go on, Ardi.
Yeah. ABD.
So from that we will get a matrix called ABD matrix. It is a really important matrix because it tells us the behavior of the composite. So the A matrix will tells us the in-plane stiffness of the structure. So it's basic in-plane properties. So the D matrix, called bending stiffness matrix, it relates the bending moments. And B matrix relates the in-plane strains to bending moments and curvature in-plane forces. So it is a bending extension coupling matrix. So I need to mention this. Normally, when we are manufacturing a composite, we don't want a B matrix because normally, by the way, most of the time, because it is not manufacturably friendly, I would say. It will warp when you take out the plate. It will warp, but in some occasions.
Sorry for interruption. Basically, you mentioned about it the symmetry of the ply composition. Am I right? If you have a symmetry ply composition according to the mid-plane surface, so we don't have the B matrices. As you can say, if you have a B matrices, I mean, in symmetry in your composite product, so it could be because of the manufacturing effects, we cannot purely flat composite material at the end of the process. What I understand.
Of course, yeah. I am talking in an ideal case in order to explain the equation or the meaning. By the way, sometimes you need an antisymmetric plate, maybe for some aerodynamic devices or unstable structures. Sometimes it happens in a really advanced applications, but it's really hard to. I think it's really hard to achieve a really, I would say, really physical behavior that you can perfectly sure about it. It needs a really big expertise. Okay, please go on.
Yeah.
Please go on. So I will just skip it because I just talking about it. You can look. So
So we
I
have
cannot
A
see.
matrix and B matrix in here.
Yeah, it is. We talked about it, so we have not a we don't have a time for explaining everything. Yeah.
Yeah, sure.
So we can move on. So another thing to increase your, I would say, efficiency in your FEM analysis, what you can do is, if you're not looking, or if some parts in your FEM analysis is in your it is out of scope, you can use effective properties of 2D laminate, but it needs to be symmetric. The A matrix needs to be symmetric, otherwise you cannot achieve it. It's a good way, by the way. So this is a VV virtual crack closure for delamination. We will show the IMP files. As you can see, I modeled here as a continuum shell, but what I've done is I am in here. I am not. It's not in my scope that the stresses in the this upper and lower plates. What I'm looking is the delamination strength. So because of that, I used effective material properties, and it increases it lowers the computational time significantly, I would say, when you compare.
Okay.
Yeah, we can go
So,
on.
failures in composites. Right.
Yeah, so it is in this failure mode, as you can see, you have a fibers in the zero direction. So most of the time for the carbon fiber, you have linear and brittle fracture, but sometimes because of the difference between the failure strains of the fibers and the matrix, sometimes it become nonlinear as well. Please go on.
Yeah.
I will say that if and I think I can say that more clearly, if you have a resin-dominated behavior, probably you will end up, or you will see, a plastic deformation, because our matrix is a plastic material, and normally the last slide, you will see that it is dominated by the fiber strength. But right now, and you will see in the other behaviors as well, it is most of the time resin strength and resin fiber interface integrity dominated.
So that's why at the end we are getting the local backlink areas.
Yes.
Like,
yeah.
Generally, we don't want to use it. Actually, we don't want a unidirectional compressive strength.
Yes.
So we actually want to do tensile strength of the fiber direction.
Yeah. Please go on, Ed.
Yeah.
So this is, as you can see, is a relatively linear, except near failure strain. It's in near failure strain, it's plastic as well. Also, it is, as I said, it's dominated by resin strength. Please go on, Ardi, because it's most of the time it's same. So as you can see, by the way, in the 90 direction, you have a 45-degree fracture surface, and the transfer shear is very similar, has a really similar profile as well. So we can go on.
Failure, shear failure.
So yeah, I think everybody did understand what I said, so we can go on as well.
Oh, this one. Yeah.
Okay, the failure failure criteria. So it is really important when you're modeling composite parts. By the way, sometimes it's misunderstood, because not every failure criteria is really good to assess a composite structure. In here, as you can see, we said that composites have between extensions or couplings. So if you use maximum stress criteria, you will understand nothing about it, or you will not see a real behavior I would say, because there's always a coupling effect between the shear stresses, normal stresses. You will see that in the other interactive failure criteria. Yeah, please go on, Ant. So in SciWoo is a interactive part, but the problem is even it is not tells about how it deformed or how it failed. So it only says that okay, it's failed. So if you are not looking for a, I would say, really detailed, or if you're not trying to determine what is my failure mode, maybe you can use it, but you need to check it with the real tests, I would say, with your finite element model as well.
So basically, we can say that the SciWoo is the general approach for the failure.
Yeah, you can use for other anisotropic materials as well. It's really general failure criteria. So yeah, we can go on.
Last one. Yeah.
Yeah, the last one. So as you can see, Hashin has Hashin has some things that it's tension fiber direction, maybe failure, as you can see in this equation. So it tells us something. It says that okay, it failed because tension fiber direction or tension transverse direction. So it is, I think it is more applicable to use when you're trying to determine the cause of failure, I would say. Okay, that's about the end. I think, yeah, that's the last
for
one.
the composite side. So thank you, Bartu, by the way. So I will continue for the thermal material properties. We don't have much time, but it's a little bit faster. So what I said that if you have doing a thermal pure heat transfer analysis, you don't need to enter the modulus of elasticity or Poisson ratio. You can only need just a simple common thermal effects. I mean, the conductivity and the specific heat and density could be enough for the pure heat transfer analysis. But if you have a good go for the advanced, like the changing the crystal structure, you need to add your latent heat or any initial heat generation, for example. So we already know that conductivity is really required for the heat transfer analysis, and you can just directly use it the isotropic or orthotropic modeling in Abaqus. Actually, I will mention about it, but here it is, the conductivity units in here. So density, of course, you need to enter your density effect to gain the which transient levels need to be taken into account, and the specific heat that this is the rate of the increase of the initial thermal energy that need to be enter actually. So this is the units. So these three material properties really depending on the temperature effect actually. Before we go on, so here it is the lots of, I mean, the common material properties, for example, steel and the copper, like that. But the accurate solution, actually, the accurate value could be obtained in total materia, because in total materia, please, if I'm wrong, please correct me, Zain. In total materia, we can actually get the temperature dependent effects on, I mean, the temperature dependent conductivity, density, and specific heat. I mean, so you can just directly get from the information from total materia. So these three effects actually really temperature dependent that need to be taken into account actually. So especially the specific heat, the higher temperature really effective, and mostly density, some metal materials cannot be assumed as cannot be changed by temperature, but we already know that there is a thermal expansion coefficient we have, so basically density also changed. But if considering the changes of the density, we can assume the same constant level, actually, if you are doing the low temperature effects. So in order to, if we talk about the simulations in the analysis procedures, we can directly just go for the 4 different approach. The sequential one is you have a stress analysis and you have a thermal effects. You can just directly map your NT11, which is equal to the nodal temperature output. You can just directly implement on the stress level and just observing the output, the stress area. But in this condition, you will not affect between the temperatures and the stress level. I mean, in the coupled analysis, it depends on it. For example, if you have a contact, and due to the contact solution, due to the contact problems, you will get the temperature change at the contact pressure area. If you have a more contact pressure, you will be more contact conductivity coefficients that you will get. So that's why you need to consider about coupled analysis. On the other hand, if you're looking for adiabatic analysis, that means if you have a forming analysis, and you can consider there will be no heat effect, but there is actually a heat effect that inelastic heat fraction. So it means that mostly the 90% of the total plastic initial energy can be converted to heat effect. So if you have a even if a cold forming, that you may be concerned about the plasticity, because of the plasticity, the initial heat effect actually. So it directly change your spring back effects and also the plasticity curve. You need to consider about it if you have a really big strains. So the last one is the everything can be happened, thermal, electrical, and the structural. This is the nugget formation, the spot welding analysis. That so it is also dependent on the current and dependent on the resistance of the material. It depends on the temperature, also lots of things in here. So it's really challenging to solve this simulation. Basically, the 3 different approach I've been just summarized in here, so you can directly just consider it, and you can easily get this presentation from Zaim actually. So the last one is simulations, forming simulations, Abaqus. So I have 4 different analysis in here: deep drawing, forging, roll forming, and spinning. Due to we don't have enough time, but I will directly just send to you these input files and the CE files, and you can directly easily look for it, because in this examples also you have a coupled Euler Lagrangian and the augmented Lagrangian methods also implement on it. As you can see, we have a analytical rigid in here, and the forming also in here. Arbitrary Lagrangian method will be implemented on here, and also and in here is a Lagrangian model, but it could be also modeled coupled Euler and Lagrangian because of the high strain values in here, and also this could be effect on the friction level is really dependent on the pressure on this analysis. Also in here we have also another analytical rigid a diform, but you can also easily model as a discrete rigid, for example this one. So you need to consider about your mesh, and you can maybe remeshing tools, using remeshing tools or adaptive meshing method, you can easily implement on it to observe the more accurate solution actually. So any question from your side? Zaim, it's your turn actually. you hear me.
Thank you very much. Today's session, and you can just finalize the next session and details for the participants, and we can close. And let's see you next week.
Okay, so take care of yourself. Okay.